Good day everyone. Today, I'll be presenting the chemistry behind semiconductor technology in modern communication system. We'll explore how chemical principles are at the core of the devices and networks we use every day. So, what are semiconductors? Semiconductors are material with conductivity between conductors and insulators. They're essential for electronics because they can control electric current. In communication system, they enable devices like smartphones, computers, satellites, and many more infrastructure to operate efficiently and quickly. In this slide, basic chemistry of semiconductors. Here are the common semiconductor materials include silicon, germanium, gallium, and arsenic. Silicon from group 4 is the most used. Gallium and arsenic, when combined as gallium arsenic, form a group 3 to 5 compound. These materials form structured crystal lattice, allowing precise control of electron movement, key to reliable circuits. Doping and conductivity. To make semiconductors more useful, we dope them, meaning we add impurities. N-type semiconductors use elements like phosphorus or arsenic to add free electrons, while p-type semiconductors use elements like boron to create holes or positive charge carriers. This process allows for controlled conductivity in electronic devices. While semiconductor materials like silicon is widely used due to its cost and abundance, but compound semiconductors like gallium arsenide or indium phosphide offer higher performance, especially for high-speed and optical application. These materials are chosen based on the needs of specific communication system. Chemical process in semiconductor fabrication. Semiconductor chips are built through detailed chemical processes like oxidation from insulating silicon dioxide layers, while etching uses acids or plasma to shape components. Diffusion and ion implementation introduce dopants. All of these require precise control and involve reactive gases and strong acid like hydrofluoric acid and hydrochloric acid. Now, let's take a closer look at the key semiconductor devices used in communication system. First, we have transistor, which are arguably the most critical components. Transistor act as both switches and amplifiers for electrical signals. CMOS, which stands for complementary metal oxide semiconductor, is used in digital electronics like microprocessor, memory chips, and logic circuits. Then there's HEMT or high electron mobility transistor. HEMTs are typically made from compound semiconductors like gallium arsenide or gallium nitride. They operate at higher frequencies and are perfect for microwave and millimeter wave applications, such as those used in 5G base station, radar system, and satellite transceivers. Next, we move to integrated circuits. These are miniaturized electronic circuits consisting of millions, sometimes billions of transistors, all interconnected on a single chip. Integrated circuits are the brain of communication devices. They handle everything from signal processing, data encryption, modulation, to power management. Another major category is optoelectronic devices, which bridge the gap between electrical signals and light. These include light-emitting diodes or LED, which converts electrical energy into light for indicators and low-speed communication. Laser diodes, used for high-speed optical communication, such as in fiber optic cables that transmit internet data across continents. Photodetectors, which detect incoming light signals and convert them back into electrical form, making them essential for receivers in optical networks. So, in summary, Semiconductor devices power almost every level of modern communication, from processing signals to transmitting and receiving them through light and electromagnetic waves. Now, let's explore how semiconductors impact real-world communication system. First, in 5G networks, semiconductors are crucial for enabling ultra-fast wireless data transfer. 5G operates at higher frequencies than previous generations, and this requires high-performance transistor, such as gallium nitride-based high-electron mobility transistor, which can handle the speed and power needed for small cell tower and beamforming technology. Without these materials, the low latency, high speed features of 5G wouldn't be possible. Next, we have fiber optic communication. This is the backbone of the internet. Data is transmitted as light pulses through glass fibers. Here, semiconductors lasers serve as the source of light, and photodetectors, often made from indium phosphide or germanium, convert that light back into electrical signals at the receiver. These materials are chosen specifically for their ability to operate at the wavelengths used in optical communication. Now, let's talk about the environmental and safety aspects. While semiconductors bring incredible benefits, it's also important to consider the environmental and safety implications of their production. Semiconductor manufacturing involves the use of toxic chemicals. For instances, hydrofluoric acid is used to clean silicon wafers and etch pattern, and it's extremely corrosive and dangerous, requiring special safety protocols. Hydrochloric acid and gases like saline and phosphine are also commonly used, which are flammable or toxic under certain conditions. The waste management from semiconductor fabrication is another major issue. Each fabrication plant or fab consumes large amount of ultra-pure water, sometimes millions of liters per day. Chemicals used in etching, doping, and cleaning need to be carefully neutralized and disposed of to avoid contaminating local ecosystem. To address this, the industry has invested heavily in cleanroom technology, filtration systems, and wastewater treatment plants. Workers wear full protective suits and robotic systems are used handle the most dangerous chemicals. In addition, regulations such as restriction of hazardous substances and REACH in Europe aim to reduce the environmental footprint of electronics manufacturing by limiting the use of harmful substances. Going forward, the push for greener semiconductor chemistry, less water usage, and recyclable materials is gaining momentum. Environmental sustainability is now a key part of semiconductor R&D. Looking ahead, the future of semiconductor technology and communication system is incredibly promising. One major area of development is emerging materials. Graphene, a one-atom thick sheet of carbon, is being studied for its ultra-high electromobility and flexibility. It could lead to flexible, transparent communication devices in the near future. It can be used in future light-emitting devices or solar-powered communication system. Nanotechnology is also playing a critical role by manipulating materials at the atomic level. Engineers can create nanoscale transistors that are faster and more energy efficient. This means the future communication chips will be smaller yet more powerful, allowing for things like smart clothing, wearable sensor, and communication devices. Perhaps the most futuristic area is quantum communication. This involves using quantum dots, which are semiconductor nanocrystals, to transmit data using quantum particles. This system promises unbreakable encryption and ultra-secure data transfer, especially invaluable in defense and financial industries. All of these innovations stem from the chemistry of materials, how atom bonds and how electrons move, and how we can engineer matter at the tiniest scale to push the boundaries of communication. In conclusion, we've seen that chemistry is not just a background science, it's the very heart of semiconductor technology. From the selection of elements like silicon, gallium, and arsenic to the complex doping and etching processes, every step in semiconductor fabrication is chemically driven. These materials are then turned into transistor, circuits, lasers, and detectors, powering everything from smartphones and fiber optic cables to satellites and future quantum networks. Semiconductors are what allow us to communicate instantly across the globe, and with continued advancement in chemical engineering and material science, the possibilities for faster, safer, and more energy efficient communication are limitless. And that's all. Thank you.